All right, so the first question I'm going to go over is the tree diagram question. So it says, suppose that 20% of athletes use steroids. Suppose that a test is available that's positive in 95% of the athletes who use steroids, but also positive in 4% of the athletes who do not use steroids. So first thing we're going to do is we're going to make a tree diagram. So we're going to use the first piece of information they give us, which is this 20% of athletes using steroids. So that means that the steroid users is 20%, which is 0.20. So if 20% of athletes use steroids, that means that the non-steroid users would be 80%, which is 0.80. Okay, so then we're going to use the next piece of information, which it says that there's a test available that's positive in 95% of athletes who use steroids. So for steroid users, it shows up positive 95% of the time, which means that it's going to give them a false negative 5% of the time. Okay, and then, but it also tells us that if non-steroid users, it's positive in 4% of athletes, which means it gives a false positive. So that would just be, it shows up positive in 4%, so 0.04, which means that it's going to be negative 96% of the time, 0.96. Okay, once we do that, we also need to find the probability of each outcome, meaning if a steroid user tests positive, that would be 0.20 times 0.95. So 0.20 times 0.95 would be 0.19. The next one, it would be 0.20 times 0.05. That's 0.01. And then non-steroid users who test positive, that would be 0.80 times 0.04. Which is 0.032. And then lastly, non-steroid users who test negative, so 0.80 times 0.96. 0.768. Oops, 0.768. All right, one thing that you can check, remember that the sum of all of these numbers should equal to 1, and that's a good way to check to make sure you had these percentages correct. So part B says, what's the probability that an athlete who uses steroids tests positive? So steroid user tests positive, that would just be this here, 0.20 times 0.95. That would be 0.19. So that means if we looked at all of the tests that we've ever done for all of these athletes, 19% of them would be steroid users who test positive, so 0.19. All right, the next question is an expected value problem. So it says a player pays $2 to play a casino game. Player spins a spinner, whatever region it lands on is what the player wins. So here is our spinner. So first thing we're going to do is we're going to calculate the expected value. So to do that, we're going to make a table. So our table consists of 3 rows. It's the outcome, the profit, and then the probability. Well, if we look at the different outcomes, we'll start with the lowest amount. So they can land on 0. They can land on 1. They can land on 2. And they can land on 10. Okay, so now let's figure out what the profit is. So this is where we have to take into account that they're paying to play. So if we land on the 0, your profit isn't 0, it's actually going to be -2 because you had to pay to play. So 0 minus 2 would give you -2. So to get the profit, we're going to subtract 2 from all of these amounts. 1 minus 2 would be -1. 2 minus 2 would be 0. 10 minus 2 would be 8. So this is the profit that you would get depending on what region you landed on. So now for probability, we need to figure out the fraction. So something that might help you with fractions here, if they aren't all the same size, it might help to pretend to cut it so they're all equal sizes. So now we can think of there's 8 total pieces. So in terms of landing on, so all of these are going to be out of 8. So landing on 0, there's 1, 2, 3, 4. So 4 out of 8, or 1/2. Landing on 1, that's 1 piece out of 8. Landing on 2, that's 2 pieces out of 8. And then landing on 10, that's 1 out of 8. So again, if they're all the same size, you don't have to worry about that. But since there's some pieces that are different sizes, it might be helpful to make them all the same size. So now to calculate the expected value, we're going to multiply the profit times the probability. So it's going to be -2 times 4 over 8 plus -1 times 1 over 8 plus 0 times 2 over 8 plus 8 times 1 over 8. So if we put that in our calculator, -2 times 4 over 8 times 4 plus -1, or you can do -1, times 1 over 8 plus 0 times 2 over 8 plus 8 times 1 over 8. So -0.125. So in terms of interpreting the expected value from part A, that means if we played this game many times, we would lose on average about 13 cents per game. We say 13 cents, well, we would say lose because it's negative, and I'm just rounding to 13 cents. So again, if we play this game many times, we would lose about 13 cents per game. All right, so the next question says, here are the measurements in millimeters of a critical dimension of an SRS of 16 of the more than 200 auto engine crankshafts produced in one day. So it gives us a bunch of measurements. Construct and interpret a 95% confidence interval for the process mean at the time of these crankshafts were produced. All right, so step 1, we're going to identify the symbols. So we know that this is a confidence interval for the mean, which means that we need to identify X bar, S, N. We can also identify big N. And then in this particular problem, since our sample size is less than 30, we're going to be using T star for this problem. All right, so I have the data here in GeoGebra. So first thing I'm going to do is I'm going to get X bar. So X bar is going to be the mean. So that's going to be 224.002. The standard deviation is going to be S.0618. N we know is 16. And this is going to be all, big N is going to be all auto engine crankshafts. And then T star, we're going to need to go back to GeoGebra. So in this particular problem, to get T star, so remember that we are doing a 95% confidence interval, which means that there's 2.5% in each tail. So to figure out what that T star is, we got to go to GeoGebra. We need to change this to student since we're using T. Degrees of freedom is n-1, so that's going to be 15. And then remember, to get the T star, we're going to type in 0.025, the amount in the tail here. So then that means our T star is going to be 2.1314. Okay, so step 2 is to identify the parameter. So the parameter, since we're using mean, is going to be mu, and it's going to be the, the mean dimension of an auto engine crankshaft. All right, so step 3, we're going to check our conditions. So the same conditions we've been checking. So the independent condition, big N, which is all auto engine crankshafts, is greater than or equal to 10 times 16, which is 160. So actually this problem tells us our population size is actually 200. So 200 is bigger than 160, so that condition's met. For the normal condition, well, since this is means, our sample size is either greater than or equal to 30, which it's not. If it's not, we can check our normal quantile plot. So if we go back to the data here, and we choose this normal quantile plot, remember what we're looking for is to be roughly linear. Since this isn't clearly curved in any direction, yes, it is kind of curved a little bit, but not so much to the point of being obviously curved. We can say that it's roughly linear. So the normal quantile plot, linear, which means that our distribution is approximately normal. And then for the random condition, it does say SRS, so SRS is stated. All right, so step 4, we're going to do our calculations. So remember the calculations for this is going to be this bottom one since we're using T star. So X bar is going to be 224.002 plus or minus T star, so 2.1314 times S 0.0618 over the square root of N. All right, so I'm going to put the second part, this part in our calculator. Remember, that's going to be our margin of error. So 2.1314 times 0.0618 divided by the square root of N. So that's 0.033. So 224.002 plus or minus 0.003. Or 0.033. Okay, so to get my lower bound, we're going to subtract. So 224.002 minus 0.033. And then to get my upper bound, we're going to add 224.002 plus 0.033. So my lower bound is going to be 223.969, and my upper bound is going to be 224.035. So now I have my confidence interval. So step 5, I'm just going to do this verbally. You're going to say, we are 95% confident that the true mean dimension of an auto engine crankshaft is between 223.969 millimeters and 224.035 millimeters. Okay, so the last question, this is a chi-square test of association problem because we're looking at two categorical variables, the anger level and whether or not the person has CHD. So we want to know if there's evidence that one's anger level based on the anger scale test is associated with one's risk for developing CHD. All right, so first thing we need to do is write our hypotheses. So since this is a chi-square test of association, we're going to say there's no association between anger scale tests and risk for developing CHD. And then HA is just going to be that there is an association. I'm not going to write the whole thing over, but there is an association. Okay, so next thing we need to do with the chi-square test, we need to calculate the expected counts first before we can check our conditions. So to do that, remember for the expected count, you got to do the row total times the column total divided by n. Okay, so we don't have the totals, but we can get them here. So if we add across here, this is going to be 190. We add across here, this is going to be 8284. The total number of people is 8474. And then we can add down. So 53 plus 3057 is 3110. 110 plus 4621 is 4731. And then 27 plus 606. That's going to be 633. Okay, so now I'm going to put the expected counts off to the side here just because I don't want to make another table. So to get the expected count for this cell right here, we're going to do the row total. So it's going to be 190 times the column total, 3110, divided by the total, 8474. That's going to be 69.73. I'm just going to round to two numbers after the decimal. And then we're going to do the same thing for here. So 190 times 4731 divided by 8474. We get 106.08. And then this one, we're going to do 190 times 633 divided by 8474. We get 14.19. And then we're going to go ahead and do the second row. So it's going to be 8284 times 3110 divided by 8474. So that's going to be 3040.27. 8284 times 4731 divided by 8474. That's 4624.92. And then the last one, 8284 times 633 divided by 8474 is 618.81. All right, so these are all of my expected counts. Okay, so now we can check our conditions. So for our conditions, we still have the independent condition. So big N would be all patients. Well, actually, it's all patients, I guess, with normal blood pressure. Is bigger than or equal to 8474 times 10, or 10 times that, I guess. That's reasonable to assume. It does have the random condition that's stated. And then the last condition for the chi-square test of association is that all of our expected counts are greater than 5, which is also met. Okay, so now we have to do our calculations. So remember the calculations for the chi-square tests. To get our test statistic, it's going to be the observed minus the expected squared over the expected. So we could do that individually, right? We could do 53 minus 69.73 squared divided by 69.73 and do that for each of the things. But remember, there is a way that we can do that in GeoGebra, so I'm going to show that now. So let me clear this out. So what I'm going to do is I'm going to put the observed count. So I'm just going to go row by row. So 53, 110, 27, 3057, 4621, and 606. Okay. And then I'm going to put the expected counts in the next column. So the ones that we calculated by doing observed minus expected. So 69.73, 106.08, 14.19, 3040.27, 4624.92, and 618.81. So just make sure the observed and the expected counts line up for each cell. Okay, so now what we're going to do is we can actually type in that formula into column C. So you hit the equal sign, parentheses, it's the observed, which is in column A, minus the expected, which is in column B, squared, which you can get by typing this, divided by the expected, which is in column B. So if you hit equals, that does the calculation. Remember, you can drag that down by hitting that, getting that square in the corner and just dragging it down. So for each one, this is the observed minus the expected squared. Remember that the chi-square test, the chi-square test statistic is the sum of all of these. So what we need to do is we need to add these all together. And you can also do that in GeoGebra by typing equals sum and then clicking on all the ones. So C1 to C6, we want to tell it to add those all together. We get 16.084. So my chi-square test statistic is 16.084. And then for my p-value, remember our degrees of freedom is going to be basically the number of categories minus 1 times the number of categories minus 1. So the row categories are CHD. So that's going to be 2 minus 1 because it's either you have CHD or you don't. And the categories for the anger, there's 3 categories, so that's going to be 3 minus 1. So 2 minus 1 is 1, 3 minus 1 is 2. So that means my degrees of freedom, 1 times 2 is just going to be 2. All right, so now let's get our p-value. So p-value, we need to use our probability calculator. We're going to use the chi-square test. We always choose greater than. Our degrees of freedom is going to be 2. And then we type in our test statistic here, 16.084. So we get a p-value of 0.0003. Okay, so that p-value means that we're going to reject our null hypothesis. So again, I'm just going to do the conclusion in words. So I would say since our p-value 0.0003 is less than alpha of 0.05, we reject HO. We have convincing evidence that there is an association between the anger scale test score and risk for developing CHD.